Welcome everyone. I'd say, let me just say that you all should be proud of yourselves for coming on the weekends to try to learn some interesting mathematics. Mathematics is a very important subject. And today I hopefully will be able to show you sort of some concepts in mathematics of nature, like how mathematics is sometimes all around you, even when you are aware of it, and how it can be used to solve interesting problems. So my name is Jeffrey Oregero. I'm a postdoc here at UCF. So let me go on a little bit. So currently I'm a postdoc in the Department of Mathematics at UCF. Before this, I was visiting postdoc at the Mathematical Sciences Research Institute, MSRI in Berkeley. And I received my PhD from State University of New York at Buffalo in 2021. So PhD in mathematics, my specialty was working on what are called integrable nonlinear wave equations. So these are special equations which arise in physics, but and also have very interesting mathematical properties. I also want to advertise MSRI, Mathematical Sciences, because they are institution for sort of building the next generation of mathematicians. So I encourage you to, if you're interested in math and maybe think about pursuing mathematics later in college, visiting this webpage, visiting MSRI, because they have really interesting programs, even starting at the high school level. So you can start participating with programs at MSRI, I believe, as early as the high school level. For developing the next generation of mathematicians. So a little bit about mathematics as a profession, right? So a lot of times when I talk to my family, I just talk to people that are not sure really what does it mean, what do I do? Obviously, most of them come with teaching, right? But really, it's a lot more than that. I'd say the first thing is really research, is trying to solve new problems in mathematics, and that could be problems that are relevant to mathematics, or some kind of problems that are mathematical problems that could be useful to study any problems in another field, say like physics or even economics. Personally, I started in economics, and once I started getting to like advanced level economics courses, I started to think how useful math was for studying economics, and the optimal allocation of right? So you want in economics, you want to you got so constrained some parts, right? You want to spend your money in the way that gives you the most happiness, right? So that's actually a constrained optimization problem. You can formulate it as a math problem, you can solve the math problem, and then you can do some economic analysis. So there's this beautiful interplay between math and concrete applications. Sometimes concrete applications formulated with mathematics. Sometimes just pure mathematical problems, breakthroughs will then lead into new advances in other areas such as physics. Yeah, so some other examples would be, so computer security would be, number theory, differential equations, planetary motion, right? Understanding the motion of the planets. Linear algebra, you have optimization problems, linear programming. Topology is like geometry. You could think of it like geometry. You have data analysis. So there's interesting people working on topological data analysis right now, and they're trying to look at large data sets and trying to understand the geometry of the large data sets in order to somehow make some predictions based on that. So it's a new interesting field. So research, that's one aspect of the job. Teaching is another aspect, right? So teaching college level mathematics courses and mentoring students, right? Sometimes you have undergraduates, right? You have work on that you're an expert in. A student might be interested in pursuing that area of research, so you might mentor students, and then of course you have your courses that you teach. And then another part is professional service, right? So you want to be a servant, you want to serve your industry. One example of that would be exactly this, the UCF Math Circle, right? Professional service. Another example might be organizing workshops. So workshops are places where mathematicians can get together and share their research together and new papers, right? So when we do research, we write research papers, and then we send those papers into journals, which are reviewed and accepted or denied for publication. Do any of you have any questions about any of anything about that? Well, just keep it in mind as you pursue it. It's a very rewarding profession, I would say. But also, there's also an mathematicians hired at engineering firms, tech firms, data analysis jobs, actuarial sciences, right? So it's a technical skill set to be good at mathematics. And when you have a technical skill set, there's a demand for people with that skill in industry as well as in academia. So one way or another, getting good at math it can only help your future. And it's also fun, and it's very rewarding when you have a hard math problem that you're struggling with, that you're trying to solve, and you stick to it and you keep working at it, and then you actually solve it. Then it's a rather rewarding feeling. Okay, so now the other part is a little bit more interesting, like as far as fun. So let's talk about some counters in mathematics. So some different topics I want to discuss. There's one, number theory, and in particular Pythagorean triples and primitive Pythagorean triples. I want to look at sequences, Fibonacci sequence and the Fibonacci spiral in particular. I want to look a little bit at probability, which are random walks. And I want to look at some complex numbers, in particular the Mandelbrot set. So in each one of these cases, we'll look at a little bit of the mathematics, and we'll look a little bit at some and we'll also see how the computer, we'll look at some computer simulations on how to analyze some of these examples as well. So there's a nice interplay between the computer and mathematics as well, especially as the computer gets more and more powerful these days. All right, so the first thing, let's look at Pythagorean triples, right? So a Pythagorean triple is a set of three positive integers, a, b, and c, that satisfy this a squared plus b squared is equal to c squared relation. Okay, so these are integers that satisfy this relation, right? This is from Pythagorean theorem. So the name comes from the Pythagorean theorem, which states that the sides of a right triangle satisfy a squared plus b squared is equal to c squared. Thus, Pythagorean triples are the right triangles with integer side lengths. So then the primitive Pythagorean triple is one in which A, B, and C are co-prime, right? So that means that they have no common divisor, right? They have no common divisor larger than 1. Now, Pythagorean triples can be calculated using something called Euclid's formula. And this formula is very classic. It goes back to Euclid, who formulated it. And it says that for any pair of integers, m and n are positive, the integers a is equal to m squared minus n squared, b is equal to 2 times m times n, and c is equal to m squared plus n squared. They form a Pythagorean triple. And by the way, you hear this name Euclid and Pythagoras a lot in this slide. Pythagoras and Euclid were ancient Greek philosophers. So, all right, so now we've introduced the concept of Pythagorean triples. Let's look at it a little bit more. Right, so I want to first maybe write down a few things. One second, I need to get my pen working. Draw. Let's send that there. All right, I just need to connect this. Sorry for the technical issue. Okay, so what the Pythagorean theorem is saying is that I have a right triangle. So this is a right triangle. And this, a right triangle, these two sides meet at a right angle, 90-degree angle. And this will be my A, and this will be my B, and this will be my C. And the Pythagorean theorem says that A squared plus B squared is equal to C squared. And now when I have a Pythagorean triple, so this A squared plus B squared is equal to C squared. This will work for any real numbers, right? If you've heard of the concept of a real number versus an integer, right? So integers, right, are just the numbers. So you might have discussed this last week. We'll say this boldface Z are your integers, and they're the set of numbers, whole numbers, right, with the negatives and 0 added. So ... means it goes on to negative infinity. -2, -1, 0, 1, 2, 3, ... right? So we're talking about integers in particular that satisfy the A squared plus B squared is equal to C squared relation. So notice no fractions here, right? Ratios of integers are rational numbers, and then you have even a larger set of numbers called the real numbers. So we're just talking about integers that satisfy this A squared plus B squared is equal to C squared property. So Pythagorean triple right, is something of the form A squared plus B squared is equal to C squared, where A, B, and C are in Z, they're in the integers, right? And then a primitive, so we can denote this typically simply as ABC, right? So A, B, C will be a way to denote a Pythagorean triple, right? And now I have something called a primitive Pythagorean triple. A primitive Pythagorean triple just has the added property, so it's everything that a Pythagorean triple is, right? So it's AB, so I'll denote it as ABC because it's a Pythagorean triple, but you also have the added property that A, B, and C are coprime. So I'm going to give you two examples. So let me give you two examples of Pythagorean triples. So both of them are Pythagorean triples that you can confirm this by using the A squared plus B squared is equal to C squared formula. But then I want to ask you, which one is a Pythagorean triple, which one is a primitive Pythagorean triple, or which one is a primitive Pythagorean triple and which one is not a primitive Pythagorean triple, right? So if I look at 6, 8, and 10, and then I look at 3, 4, and 5, you can check, obviously the 6, 8, and 10 is larger numbers, but you can square 6 squared plus 8 squared, right? Add them together, it's equal to 10 squared, and also the 3, 4, 5. Right? So you can see that they're integers that satisfy A squared plus B squared is equal to C squared. But now I want to ask, is 6, 8, 10 a primitive Pythagorean triple? Yes or no? No. Not, let's call it PPT. Not Pythagorean, primitive Pythagorean triple. Why? What's the definition? To be primitive Pythagorean triple, they can't be coprime, right? Or they have to be coprime, sorry. And what 6, 8, and 10 have a common factor, right? And what's that? 2, exactly. So while it's a Pythagorean triple, it's not a primitive Pythagorean triple. What about 3, 4, 5? Is that a primitive Pythagorean triple? Yes or no? Yes, because they only have 1 as the common factor. So yes. Right? So we get the concept, right? Pythagorean triple is A squared plus B squared is equal to C squared, where A, B, and C are integers. Primitive Pythagorean triple is A squared plus B squared is equal to C squared, where they are coprime integers, right? So Now that's also kind of, these just seem a bit random, right? Like these are just numbers that satisfy that property, and that's interesting and that's nice. But it turns out that these primitive Pythagorean triples, if you plot them on a computer, interesting phenomenon that people really aren't sure why that's the case. Or maybe someone does, and I'm just not aware that they know. But I know that however you look at it, it's an interesting phenomenon that these primitive Pythagorean triples all live on these parabolic arcs, right? So now if I wanted to ask a computer how to find primitive Pythagorean triples or Pythagorean triples, right? Something that like along the line of an algorithm for generating these primitive Pythagorean triples would be useful, right? So what do I mean when I say an algorithm? So like math has one side of it which is rather abstract, and you have to be creative to answer problems. But then there's just another side of it which is force calculation. But sometimes force calculation is for us to do, but easy for a computer to do. So an algorithm is some step-by-step process where you can tell a computer do steps A, B, and C. It'll give you a result, right? So one thing that's one algorithm useful for Pythagorean triples is, and primitive Pythagorean triples, is Euclid's algorithm. So what does Euclid's algorithm say? Euclid's algorithm says the following. Assume A and B are positive integers. If you can't read something, I'm kind of hunched over, just let me know and I'll read what it says. With A less than or equal to B. We like lots of symbols in math. Then the greatest common divisor, GCD. So the greatest divisor of both the numbers A and B. So the GCD of A and B is equal to the greatest common divisor of A and B minus A. And so what you can do is you can continue this process until both numbers are the same. Okay, and that's going to be your GC, your greatest common divisor, right? So you can try, on your own if you'd like. You can try the GCD of let's say 16 and 24. Right, so you can there's other ways of doing this, of course, but what if you think a nice way of doing this is, remember, this is a nice way for programming a computer to find the greatest common divisor between two very large numbers, let's say, right? So you can apply this algorithm. You write 24 minus 16. You just keep subtracting the smaller from the larger until you get to the point where you have the same number in parentheses. And what do you get that the greatest common divisor between 16 and 24 is equal to? Anyone? 8. Yes, exactly. So the GCD between 16 and 24 is 8. Now, what happens if you keep subtracting and you get down to the number 1? That would mean that they are coprimed, right? So that's useful for primitive Pythagorean triples. Okay, so now you can go onto the computer, right? And you can use now this Euclid's algorithm to give the computer a list of commands to generate primitive Pythagorean triples and Pythagorean triples. So this first picture is a picture of the first 5,000 Pythagorean triples, right? So we have A and B, basically the horizontal x-axis would be your A's and the vertical axis would be your B's. And this plot is then, we make it symmetric left, right, up and down, just in order to see this parabolic nature. Now notice you see these lines, right? You see these lines emanating from the origin. Well, that makes sense because if I take any constant multiple, so take a 2 something that I know is Pythagorean triple. The p constant multiple of that Pythagorean triple gives me another Pythagorean triple. Right? If you know, you can try this by taking, suppose you know that a squared plus b squared is equal to c squared. What does that tell you? That k squared and satisfy, right? So you will see that generates another Pythagorean triple. So that's why we have the lines. So the lines are easy to deduce, why we see these lines sticking out of the origin. But what's more interesting is that we see these, if you sort of, hopefully back, you can see it, you see these curves, right? Sort of, there's some curve, these are parabolic curves right here that are also seem to be forming. And the fact that you can see them in this, just this pattern of all the Pythagorean triples means that they're happening quite often. So now what I want to do, instead of plotting all of the Pythagorean triples, I want to plot just the primitive Pythagorean triples. So now if I plot just the primitive Pythagorean triples, so again, I give the computer a set of commands such that the properties of having the greatest common divisor of A and B 1, right? So co-prime, that's going to get rid of all of the sort of all the Pythagorean triples and just give me the primitive Pythagorean triples, and then I get this plot here. And now you see that the arcs are a little bit more clear, right? You can see that these primitive Pythagorean triples are sitting on families of parabolic curves. Right? So going back to the slides, I'm going to give you the nicest picture of this that I've seen so far, and that's this picture right here. This is actually on the Wikipedia page, and this Adam Cunningham is a friend of mine, and John Ringland is a professor in Buffalo who generated this plot. So this is a plot of these curves for Euclid's formula, and the triangles that you see here are the primitive Pythagorean triples, right? And you can see that they're all lining up. Some of these Pythagorean triples all on these parabolic arcs. Very interesting pattern. It's a pattern in math that's pretty surprising. Why is that actually the case? Notice that there's some gaps. So we can't say that every intersection point of these two parabolic curves is necessarily a primitive Pythagorean triple. And I don't think we know for sure that all of the primitive Pythagorean triples lie on the set of points. But at least we know that there's this interesting behavior that's worth pursuing further. Right? Why don't we do that in particular? So the computer is giving you some information that these parabolic curves are useful for understanding primitive Pythagorean triples. Now the mathematician why is that the case, and try to study this further and try to do some research and see if they can answer that question. Questions about this? So that's primitive Pythagorean triples and a pattern associated with primitive Pythagorean triples. Here's some questions. You could try this. So here, find the greatest common divisor of 238 and 1020. If you have like your phone, maybe, and you want to do that, you just keep subtracting the larger from the smaller from the larger, right? And you could keep doing that and doing that and doing that until you get an answer. Another question, which is a little bit more thought-provoking, is, well, you have Euclid's formula for a Pythagorean triple, right? So now suppose that you have two positive integers, m and n are both odd. What does it mean to be odd, right? It has the form like 2x plus 1, right? So it's not a multiple of 2. But suppose I have m and n are odd numbers. So why is it when m and n are odd, a, b, and c is not a primitive Pythagorean triple? The way that you could think about this is what happens when you multiply two odd numbers together. What happens when you subtract two odd numbers from each other? Right, so that will give you some answers. Obviously, b is even, right? Because it's 2 times m times n. So whatever m times n is, when I multiply by 2, I automatically get. Does anyone have an answer for tried the first one? Yes? No? The greatest common divisor. So 2 is a common divisor. So what's the greatest common divisor? Good guess. Yes. No, close. Yes. You're just about there. All right, it's 34. Was that your answer? I'm sorry, I missed you. I'm sorry. Next time. So it's 34. And the way that you can see this is I mean, it takes some time. You do, right? You just keep subtracting 1020 minus 38, and then you do the next step, I'm sure I made a mistake the first time that I did it also, just sitting down doing it, right? But if you're interested into seeing the answer, I'm happy afterwards to discuss with you further. What about the other problem? Why could this not be a primitive Pythagorean triple? This one is you gotta think about numbers a little bit for this problem. Anyone have an answer to this second one? Well, let me ask you a question. If I have let's say, so we're told that m and n are odd, right? So if m is odd, if I take an odd number and I multiply by an odd number, what do I get? Think of 3 times 3 is 9, right? So an odd times an odd is an odd number. So if m and n are both odd, m squared and n squared are both odd. What happens if I subtract 2 odd numbers? What do I get? An even number, right? Like 7 minus 5 is 2. Right? So you subtract 2 odd numbers, you get an even. So that tells me that A is even. Same thing for C. M squared and n squared are the squares of odd numbers, which are odd. And I add them together, then I get an odd number, so an even number. So C is also even. And B is clearly even because it's being multiplied by 2. So A, B, and C must be even, so they're not co-prime. So they can't be primitive Pythagorean triples. A way that you would kind of do this carefully is you would represent the odd number as like 2 times x plus 1. And if you represent an odd, so x can be some integer, then this is always going to be the form of an odd number. And then if you square that, and then you try, so if this would be your n, and if 2y plus 1 was equal to your n. And if you try working with that as your m and n, you'll see at the end that A, B, and C all have 2 as a common factor. All right, next topic, Fibonacci sequences. So in mathematics, a sequence is an ordered list of numbers, possibly infinite. So so in fact, the counting numbers would be 1, 2, 3, 4, 5, 6 of numbers, right? Because there's a rule that tells me what the next number is based on the previous number, right? So a sequence is an ordered list of numbers, possibly infinite, where repetition may occur. I could have the sequence 1, minus 1, 1, minus 1, 1, minus 1, right? So it's just a list of numbers. So a special sequence is called the Fibonacci sequence. So the Fibonacci sequence has the form that the first f sub 0, so the first element of the sequence is, do you see my cursor here? And so that's a 0. Then you're told the first element is 1. Now, what does this mean? F sub n is equal to f sub n minus 1 plus f sub n minus 2. We'll take n to be 2, right? Because n is greater than 1. So take n to be 2. That tells me that f2, so that would be the third element in the sequence, is f1 plus f0. So a Fibonacci sequence tells me that the next element in the sequence is the sum of the previous. That's the rule that generates the Fibonacci sequence. So the Fibonacci sequence appears first in Indian mathematics. The sequence is named after Italian mathematician Fibonacci, who used it to study the growth of rabbit populations. So I'm not sure why or how he was, well, I know why he was probably interested in rabbit populations, not sure how it was used in that respect. It comes up in popular culture a lot, and it's the golden ratio. I always like to talk about the golden ratio. The Mona Lisa satisfies the golden ratio. That's some sort of spatial symmetry that's supposed to be appealing to our eyes, I would say. But it's amazingly, it's found throughout nature. And where is it found throughout nature? It's found throughout nature in terms of these logarithmic spirals. So these logarithmic spirals, these spirals that you see are related to basically the Fibonacci sequence, and I'll show you that how that is next. But you see here what we have is a flower, right? And if you look into the second flower, you can see it's the hearts of the deck, but certainly spiral sort of behavior going on here. Then you have the seashell has a spiral form. You might have seen some shell like that on the beach. We live in the Milky Way galaxy, right? That's a spiral galaxy. So galaxies are puzzle for these and then hurricanes. If you're in Florida, hurricanes, they are also have these Fibonacci spirals. Actually, this is a nice picture because it's, if you look closely, you can see the spiral is actually drawn over top of the hurricane. So here, this spiral form that is occurring all throughout different random places in nature. So this weird Fibonacci sequence. How do I see the Fibonacci sequence as a spiral, right? So let's go back to some writing. I believe that's here. So the Fibonacci sequence. So remember, the Fibonacci sequence is given by this rule. So f of 0 was equal to 0. F of 1 is equal to 1. And then f of n is equal to f of n minus 1 plus f of n minus 2. And here n is greater than 1. So maybe we'll list a few. So let's list a few elements. So we know f of 0 is 0, and we know f of 1 is 1 by definition. So that's information given to us. So that tells me that f of 2, and you can even disregard this if you just remember it's the sum of the previous two. So it's 1 plus 0. So f of 2 is 1, right? And now f of 3 is equal to what? 1 plus 1, which is equal to 2. And f of 4 is equal to 2 plus 1, which is equal to 3. And so here's a question. In fact, I think I had it on my slides, but I'll just ask it now since we're doing it. What is f sub 12 equal to? So you'll see these numbers grow fast, right? So they start off small, but because you're taking the sum of the previous two, they're growing. So this will take a few additions, right? So f of 5 is 3 plus 2. F of 6 is 5 plus 3. No? Yes? Yes, 89. F of 12 is 89. So everybody see why? We could do a few more. So like f of 5. All right, so f of 5 is 3 plus 2, which is equal to 5. F of 6 is equal to 5 plus 3, which is equal to 8. F of 7 is equal to 8 plus 5, which is 13. And you just keep generating the sequence. Okay, let's look at how the Fibonacci sequence can be related to this, this logarithmic spiral that I was showing you, which appears in nature, right? So I'm going to draw some squares. So remember, f of 0 is 0, right? So I'm going to just pretend like this is the 0 point here. And now I'm going to draw the next term in the Fibonacci sequence is 1, right? So now I'm going to put this into a square whose side lengths are 1. And then the next term in the Fibonacci sequence is also 1, right? So it's 0, 1, then 1 plus 0, so that's also 1. So I'm going to draw another square whose side lengths are 1. And now the next term in the Fibonacci sequence is 1 plus 1 is 2. So I'm going to draw a square now whose side lengths are 2. Right? And now if I continue this, the next term is 2 plus 1 is 3. So if I make this a square with side lengths 3, I have something that looks like that. And now 3 plus 2 is 5. So if I make something with a square with edges side lengths 5, so 1, 2, 3, 4, 5, then I get something that looks like this. Okay, thank you. 5. Like that. And let's do one more with side lengths 8, right? Because 5 plus 3 is 8. So you see all of these squares are being generated by the terms in the Fibonacci sequence. So let me be careful here. 1, 2, 5, 6, 7, 1, 6, 7, 8. And that's going to give me my 8. Okay, so that's nice, but what does that have to do with spirals? Well, now if I take this rule where I draw arcs along each of these squares, so let's do a different color, and I'm going to start at the 0 point here, and I'm going to make an arc through the points like that, and then I'm going to make another arc through the next square like that, and then I'm going to make another arc through the next square like that, and then I'm going to make another arc through the next square like that, and I'm going to do another arc like that, and then finally I'm going to do the last arc something like that, and that's giving me the Fibonacci spiral. And I can keep doing this, and it would keep spiraling larger and larger and larger. Okay, so the Fibonacci sequence is this sequence of numbers that you could relate to this interesting spiral which you see in nature. So in the interest of time, let's continue on to the next topic. So let's talk a little bit about random processes. Random processes. So maybe I should start with notes right away because this is a little probability. So let's talk about some definitions of probability. So probability. Probability is very much all around us, and then stochastic processes are basically events that happen across time in random ways. That's also all around us, right? Things are very much related to randomness. So a few definitions. So first, let's think broadly, classically, what do we think of probability? Well, basically, you could think of this as an experiment that produces a number of outcomes. And then we call the set of outcomes, so the set of things that could happen, the set of outcomes is called the sample space. It's called the sample space. And then some subset, so a smaller set within the larger set, right? Some subset of the sample space is called an event. Okay, so usually definitions in math are rather abstract, and we like to give our minds some intuition of what they mean by looking at some concrete examples. It's a common practice at all levels of math is to do exercises such as this. So let's look at an example. An experiment could be as simple as a coin flip. We've all done this before, right? So you have a coin flip, right? So what's the sample space? The sample space is basically, well, what can happen if I flip a coin? I can have a heads or I can have a tails, right? So now we can denote the probability of a heads, right? What's the probability of a heads? Well, 50%, or we're gonna do it in terms of fractions here. So 1/2, right? 50%. So you have, it could either, you flip a coin, it can either be heads or tails. So there's two things that could happen, right? So there's two elements in the sample space. A successful event would be getting a heads. So there's one heads out of the two options. So the probability is 1/2, 0.5. Okay, what about, let's try to keep the definitions. What about something a little bit more complicated? What about roll of a die, roll of dice? So roll of a die. Right, so here you would have, what's the sample space? It's a 1, a 2, a 3, a 4, a 5, and a 6. Right, so here the 1 is like that, the 2 is like that, the 3 is like that, the 4 would be this, the 5 that, and the 6 is what? This. Okay, so this again, this is the sample space. When you roll a die, these are the options that you have that can occur. So now let's say, what is the probability of rolling a 2? So P2 means the probability that I roll a 2. 1 in 6, because you have, there's 1, 2, there's 6 options, so it's 1/6. And what's the probability, let's say, of rolling an even? 1/2. Now, why is that? Because what are the evens? 2, 4, and 6. So a successful outcome would be getting a 2, a 4, or 6. So there's 3 successful outcomes. The sample space has 6 elements. So that's 3/6 or equal 1/2. So now I'm gonna propose an experiment. This is something called a random walk. So now you tie something to the problem. You tie some time-dependent process to this probability. So let's say that you're standing in a room and every minute you flip a coin, and the coin comes up heads, tells me I take a step to the left, and the coin comes up tails, that means I have to take a step to the right. Right, and you do this every minute. You play this game where you flip the coin, you take a step to the left or take a step to the right, based on whether you get a heads or tails. And you do this, let's say, for 10 minutes. So you do this 10 times. So we can model that. We could draw a picture of what's happening here, right? So let's pretend. Let's look at this. Actually, wanna. So let's say that this is my time, right? And let's say like this is my spatial coordinate, right? So we'll locate where I am in space by time. And let's say I start off at this, point in the room right here, right? And then so I have times like 1, let's say 1, 2, and 3, right? So I can have a 1 time 2 and a time 3. Right, so after 1 minute, I flip a coin. That means I step left or right. So that means I can go like that, or I can go like that. Right, so at 1 minute later, I'm either 1 step to the left or 1 step to the right. Now, 2 minutes later, I flip the coin again. I go either 1 step to the left or 1 step to the right, 1 step to the left, 1 step to the right. So notice these 2 points meet right here. And then I play this game one more time, and then I go one more step to the left, one more step to the right, one more step to the left, one more step to the right, one more step to the left, one more step to the right. So at the end of the game, those are the places where I can be, right? And this is a random process, right? So basically my location is random in time. So maybe the true nature of what happened was something like that. But that's not what has to happen, right? It could also be that that happened. If you were to play this game for infinite time, to infinity, do you know where you would expect to end up at the end? Not where you actually would end up, but where you would expect to end up. Basically nowhere, because the probability of going to the left is the same as the probability of going to the right. And so the expectation that you went anywhere, the expectation is that you stayed still, basically. That doesn't mean that's what actually happens. That's just if you were able to run this experiment all the way out to infinity, that's where you would expect to go. This is also a model of like stock price fluctuation in some very general, in some reduced sense. You think the same thing. You have a stock price at the end of every day. The stock, you'd say, can go up with 50% probability, or it could go down with 50% probability. And then the next day, it could go up with 50% probability, or it could go down from 50% probability. Usually the actual model for a stock price fluctuation is this random noise event coupled with some long-term average growth rate. So it would be a random process like this random walk, right? This is called a random walk. Coupled with some long-term expected growth rate in the stock. So it would be a random walk with a drift. So you don't just end up where you started at the end. So one of the reasons why, so this would be, I guess, an example of the lack of a pattern, right? There's things moving randomly and different outcomes can occur. But what's interesting physically, like in statistical physics, sometimes random motion of very small molecules lead to macroscopic deterministic behavior. It's actually how the diffusion of heat works. So randomly, your molecules are moving around randomly and bumping into each other, but that's causing them to spread out into space, which is called diffusion. And that's why heat goes from, the hot molecules are excited, they bump into each other and they move into the colder regions of space. So heat sort of dissipates into the room. So let's look at some computer simulations of this. So here's the random walk that we just, so if I execute this code, you'll see a picture pop up. That's a random walk, basically. It's a random. The only thing that I'm doing, I'm kind of cheating a little bit. But I'm saying I don't want it to go out. So if you see something like that, means that I'm cheating a little bit, because that little that should have gone up further. I didn't want the window to get excessively big, but you can see what's going on here is I'm doing 100 samples, and every time I either go up by one or down by one. And what you'll see is every time I do this, the picture will be slightly different. It'll never be exactly the same, because it's a random event, and this process, this random process, this stochastic process is governed by randomness. So we don't expect to get the same thing. Likewise, we can do, again, this is just a mathematical model, just telling a computer to do a random walk, and I'm going to generate something that's going to look sort of like stock price data. All right, so it's kind of already there. But you see, every time it'll change a little bit, and that could be your stock price. Right, and that's got nothing to do with any kind of actual data. That's just the random process of going up and down randomly day by day. Okay, but remember, there is a little bit of cheat here, because there is some long-term growth associated with the true stock value. So here we could do a 2D random walk, but I want to get to the most interesting one. So that's a 2D random walk, right? So now instead of just going left or right, I can go left or right backwards or forwards. So that generates a 2D random walk. But what about a 3D random walk? Hang on a second. Just want to regenerate the kernel. So this is an example of the 3D random walk. So now what I've done here is like 3 molecules in a box, and they're all assigned to sort of probabilities that they can move around space randomly. And that's a 3D random walk for 40 different molecules in a box. But what you see is that, what are you doing? So they're localized, but when they start moving around randomly, they wind up taking up the entire space of the box. They're bumping into each other and they're spreading out. That's an example of a 3D random walk. So it is 3 o'clock. I had one more example of another pattern in nature. So maybe I will, let me see what I want to do here. Let's go back to the slides. So some examples again for random walks and basically stochastic processes in general would be this Brownian motion, which is the path traced by a molecule as it travels in a liquid or a gas. Stock price fluctuations, neuroscience, that's the model of cascades of neurons firing in the brain. And then computer science, random walks used to estimate the size of the internet. Here's a cool sculpture. I believe it's right? Yes, the quantum cloud sculpture in London. I was in London. I should have looked for this. Anyway, so what's interesting here is that you can see random walks. This is basically what we were looking at on the computer simulation just a minute ago. And here, what they did is they used computer-generated random walk and made a sculpture based on the computer-generated walk. Now they used, you see the person in sort of in the center, which is really fascinating. When I saw that, I was really excited. I was like, oh, so to get some pattern like that, the randomness is like really very, very small chances of something like that happening unless you wait for long periods of time, very, very long periods of time. So I was excited, but then I looked into it a little bit more and I found out that they actually used some initial conditions, so some initial starting points that would give them some shape that looks like the person, and then you would come out and evolve randomly. So it's cool. Sculpture. The last thing I was going to talk about, but I think because we have to do our plans, we can skip this part. This was on called the Mandelbrot set, and I will say that's the Mandelbrot set. It's a fractal geometry. It's a fractal geometry, and you've probably seen this on these are very popular pictures. So I'm sure you've probably seen pictures of this before. So this fractal geometry is the self-similarity. So as you zoom closer and closer, you'll see it starting to repeat itself over and over again. And basically, this picture comes from this function in what we call a complex scheme. So I'm going to talk a little bit about what this means, this function, f sub b of z equal to b squared plus c. And that picture, the Mandelbrot set, is the set of complex numbers that keeps the composition of this function bounded. So if you look at that, if you take that the set of points where this operation is bounded is this this Mandelbrot set. In this example of fractal geometry. So I'll stop here because I believe. All right, so to make it to your